Alright, so we're going to finish chapter 18, hopefully with this video, and we're going to start with resistors in a circuit. So the last video was dealing with capacitor combinations. We're going to deal with resistor combinations. And we're going to start out with resistors in series. So those of you who are in the lab, we were using a circuit simulator, and one of the first exercises we did was putting two bulbs in series with a battery, and then in one of the experiments we used the ammeter to measure the current. Now you saw those little blue spheres traveling around the circuit. They were all traveling at the same speed everywhere in the circuit. So if we have two or more resistors in series, the current going through them is the same. They're all on the same path. Again, we're kind of talking about the water analogy. Think of these resistors as dams in a river. If you dam up a river, it slows the entire river down, right? The current in the river is going to be traveling at the same speed. So we know a resistor is going to slow the current down, and a potential is going to increase the current, right? So the end of chapter 17 we were dealing with Ohm's law, right? And so we saw the relationship between potential difference or voltage, current, and resistance. And so we're taking two resistors in series, and we know that the current through those two resistors is going to be the same, right? So I1 equals I2, okay? Which is also the current going through the battery. We use the term through loosely. There's a chemical process inside the battery that maintains a potential difference. So there's not necessarily the same type of current going through the battery, but for our purposes, that's how we're visualizing it. So the current would be the same everywhere through the circuit, especially through these two resistors. Now let's say we gave them different resistances, R1 and R2. So we're going to use Ohm's law and Kirchhoff's junction or loop rule, excuse me, and that is the voltage across or supplied by the battery, right? The potential difference supplied by the battery. Let's say I had a battery connected at points A and B, is going to be equal to the sum of the voltage drops across the two resistors, right? So delta V1 plus delta V2 has to equal the potential difference across the battery. Think of it as the bulbs or the resistors have to use up all the energy that the batteries provided. You can think about it that way. So that's the loop rule. So we're using the loop rule in conjunction with the fact that we know the current has to be the same everywhere. So I'm writing delta V1 and delta V2 in terms of the current going through the resistor and the resistance, right? So this is V equals IR, V equals IR. But the current is the same, so we're factoring out that current. So this R1 plus R2 is the equivalent resistance of both resistors, okay? So that's the equivalent of both resistors. So we can simply add up the resistances and get the equivalent resistance. So that's our rule for series resistors. If you notice, it's kind of backwards from capacitors, right? When we have capacitors in parallel, their equivalent capacitance is just the sum. So it's different for resistors in series, but the formula is the same. It's just a simple addition, okay? So for n resistors in series, the equivalent resistance is just the sum of those, the individual resistance of each resistor. So that's nice. We're going to look for 2, 3, maybe 4 resistors in series, and we can, when we go to collapse our circuit again, we can just draw that as one resistor with an equivalent resistance. That's just the sum of all those resistors on the path. Okay, so that's our rule for series resistors. All we've got to do is add them up to find their equivalent resistance. So now we're going to deal with resistors in parallel. So that was another simulation we did in lab, was we connected two resistors in parallel. Now we had to take the voltage reading across each individual resistor. So what we realized was that if we had two resistors in parallel connected to a battery, again, let's say we have a battery connected at point C and D with a voltage applied. When we took the voltage across R1, we got the voltage of the battery. When we got the voltage across R2, we also got the voltage of the battery. So these two resistors are acting like one resistor that's using up, quote unquote, the voltage applied by the battery. But we know that their currents are different. Kirchhoff's junction rule says the current in has to equal the current out. So that means the current gets split between these two paths. Okay, so these currents are different. Okay, they might be the same if the resistances of these resistors were the same, but let's just say for the sake of this example, R1 was not equal to R2. So we would have different currents going through each of these paths. They're going to recombine here at this junction and then become I again. So these two terms, V over R, they represent the individual currents that are going through each resistor. Right? See, this is Ohm's law. I equals V over R. So this total current has to be equal to the sum of these two currents. And I'm rewriting I1 and I2 in terms of the voltage across the resistor and the resistance. Okay, so that's V1 over R1 plus V2 over R2. But I know from the lab and our voltmeter readings that V1 and V2 are both the voltage of the battery. So I can write that as V sub CD. So now the numerators are the same term, the voltage supplied by the battery. So if I factor that out, I get 1 over R1 plus 1 over R2. If I rewrite this, the total current, I'll come back here to my derivation. If I write that I as the total current through that entire system, it's equivalent to the voltage of the battery divided by the equivalent resistance provided by those two resistors. So this term right here, it's V sub CD in the slide. This term right here is equivalent to this. So that means we can cancel out this V bat. Right, they're on both sides of the equation. I can divide both sides by V bat, and then I get, on the left side, I get 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over Rn for n resistors in parallel. So we notice that our rule for parallel resistors is similar to the rule for series capacitors. So we've got the same rules for capacitors and resistors, they're just applied differently depending on how the resistors or capacitors are combined. So parallel resistors, we have this rule right here. Okay, and again, this is written as the sum of the inverses of the resistances to the -1. So I like to write it like this, much like I did with series capacitors. 1 over the equivalent resistance is the sum of the inverses of the resistances of resistors in parallel. So again, the rules look familiar. We just have to apply them differently for resistors than we do capacitors. So let's start with another basic example. So I've got a combination, much like the first capacitor example. I've got a few resistors in parallel, the 18 ohm, the 9 ohm, the 6 ohm resistor, and these resistors are in series with the 12 ohm. So I'm going to do the same thing. Okay. The difference is I'm going to find the equivalent resistance. I want to find the current going through every resistor, and I want to find the voltage drop across every resistor. So the process is going to be very similar. We're just using Ohm's law instead of our formula for the charge on a capacitor. So we start by collapsing the circuit. I'm looking for 2 or more resistors that are either directly connected in series or directly connected in parallel. And this is pretty evident to me that I'm going to combine these 3 resistors, right? Because they're all in parallel. There's nothing else really inside this component, right? They're all three directly connected in parallel. So I'm going to add up these resistors in parallel, and then I'm going to redraw my circuit. So I take the 18, the 9, and the 6 that are in parallel, and I add them up. So I have to use my reciprocal rule because they're in parallel. So they're nice denominators here, right? I don't really have too much trouble finding a common denominator in this case, especially when I'm adding more than two fractions together. You know, I like to do it this way. So again, I'm leaving my units in the denominator the whole time because that is going to remind me at the very end that I still have to flip this fraction to find the equivalent resistance. So I get 1/18 plus 2/18 plus 3/18. That gives me 6/18 reduces to 1/3 ohms. So the equivalent resistance of these three resistors in parallel is 3 ohms. And that's kind of something strange that we recognized in lab, is that the more resistors you add in parallel, the greater the current was going through the battery. Because when I'm adding resistors in parallel, I'm actually decreasing the total resistance that the battery is experiencing, right? So I've got these big resistors, right, 18, 9, and 6. Combining them in parallel gives me a total resistance that's less than the resistance of just one of those resistors, right? Which is crazy. But you can think about it as, you know, if you had a pipe of water and then you split it into 3 pipes, there's more opportunity, right? There are more paths for the water to flow, so you have more choices. So that's actually going to increase the rate at which water flows through. And the same thing is happening here with parallel resistors. So I'm going to redraw my circuit. I still have this 12 ohm resistor over here, but those three in parallel now have an equivalent resistance of 3 ohms. So now my diagram looks like a 12 ohm resistor and a 3 ohm resistor in series. So with resistors in series, all I have to do is add them up. 12 ohms plus 3 ohms is 15 ohms. So now, just like with my capacitor circuit, I'm left with a battery and a resistor. Once I get to this point, I'm looking for the current that's going through the battery. Now, we'll see this in a couple examples. The current that's going through the battery is going to be the same current that's going through every resistor that's on the same direct path as the battery. So if you're a resistor and you're directly connected to the battery, you're going to have the same current going through that resistor as is going through the battery. So that means I take the voltage of the battery divided by the equivalent resistance. Voltage of the battery is 30 volts. The total resistance of the circuit is 15 ohms. I've got a 2 amp current. That's a 2 amp current here on this side of the battery, this side of the battery, and through the 15 ohm resistor. But if I go back to my original drawing, the current that's going through the 12 ohm resistor is also 2 amps. So usually what happens is if you find that total current that's going through the battery, there are going to be some resistors that are on the same path, and you can actually say, well, if this is the current going through the battery, then that's the current going through all those resistors that are directly connected to it. So that's what I found here. I actually found the current going through the battery and the current going through the 12 ohm resistor. Now the total current going through my 3 ohm resistor system, which is 3 in parallel, is also 2 amps. So the junction rule tells me that there's 2 amps going in and then there's 2 amps going out. So that 2 amps has to be split up between these 3 resistors. And so I'm going to use Ohm's law. These numbers are nice. Maybe you could figure out like a proportionality or something like that. I like to play it safe. I'm going to use Ohm's law for each of these resistors to find how much current is going through them. So I've got the current going through the battery and the 12 ohm resistor and the 3 ohm system. So I expand one step. I'm going back to my 12 ohm and my 3 ohm. What I want to do here, I need the voltage drops across both of these resistors, because the voltage drop across this 3 ohm is going to be the voltage drop across all three of these because they're in parallel. So I'm going to need that to find the current going through each resistor. So I'm using Ohm's law to find the voltage drop across the 12 ohm resistor and the 3 ohm resistor. So V equals IR for the 12 ohm resistor. I know there's 2 amps going through the 12, and I know its resistance, so I get a voltage drop of 24 volts. For the 3 ohm resistor system, I know the current that's going through it, I know its resistance, and so I get a voltage drop across the 3 ohm system of 6 volts. And the loop rule tells me that they should add up to 30 volts, the voltage supplied by the battery, and they do. 24 plus 6 is 30. So I'm doing good so far. Feel good about my answers. All my rules are evident here, right? So the loop rule holds, and so Ohm's law is giving me good voltage drops across the resistors. So now I'm going to expand my 3 ohm resistor system, knowing that the voltage drop across each of these individual resistors is 6 volts. Right? They're resistors in parallel. They have the same voltage drop across them as the 3 ohm resistor system. So I'm going to use 6 volts for the voltage drop across each of these, and then I'm going to find how the current is split. So I'm using Ohm's law, I equals V over R, for each individual resistor. So the voltage drop across the 18 ohm resistor is 6 volts. Its resistance is 18 ohms. I get 1/3 of an amp, which is less than 2, so that's good. I should never get anything more than 2. So the current across through the 9 ohm resistor is the voltage, again 6 volts because it's in parallel, divided by its resistance 9 ohms, and I get 2/3 of an amp. The final resistor is a 6 ohm resistor. It's got a 6 volt voltage drop across it, and its current is 1 amp. So I've got 1/3, 2/3, and 1. They add up to 2. Now again, this makes sense, right? This has a much higher resistance than the 6 ohm resistor, so there's less current, right? Actually 1/3, right? 3 times the resistance, 1/3 the current. Okay, so you see that the current gets progressively slower for each path that has a higher resistance, right? So you've got 1/3, 2/3, and 1. And again, just like I did with the capacitors, I have these handy, right? Most of the time we know the resistance, right? So this might not be used too often, but it's still kind of handy to have. So I'm mainly going back and forth between these two equations here to find voltage drops across each individual resistor and the current going through them. Alright, so let's look at our next example. So we've got a lot of 5 ohm resistors. The circuit looks a little bit different, but again, I want to collapse the circuit. I want to turn all of these resistors into one resistor with an equivalent resistance so I can find the current going through the circuit. So I've got a junction here and a junction here, right? So if there's anything split by a junction like this, I don't want to combine anything that's split by a junction just yet, right? Unless they're clearly 2 or more resistors that are connected in parallel and don't have any other components with them. So in this case, I'm looking for some resistors that are connected in series. And they don't look very close to each other in the diagram, but if you notice, this 5 ohm resistor and this 5 ohm resistor are on the same path. Right? So they're in series. So I'm going to add those two up, and I'm going to redraw my circuit to make this a 10 ohm resistor. Now what I did, I have a lot of resistors that have the same resistance, so I labeled them A, B, C, D, and E. Okay, just to kind of keep track when I'm looking for the voltage drops and the currents. So I've got these two in series, nice and easy. You just get to add them up. 5 plus 5 is 10 ohms. So I'm redrawing my circuit. Those two 5 ohm resistors add up to 10. Now that I redraw my circuit, I see that my new 10 ohm resistor is in parallel with this 5 ohm resistor. Okay, so this 10 and this 5 are in parallel. So I'm looking for the equivalent resistance of these two resistors. So 1 over the equivalent resistance. This isn't the total equivalent resistance. Maybe I should have given that a different subscript, but this is just the equivalent resistance of this 5 and this 10. So 1 over 5 ohms plus 1 over 10 ohms. So I add these two fractions together, I get 15 over 50 ohms, which reduces to 3/10 of an ohm, or 3 over 10 ohms. My units are still in the denominator, so I got to remember that I have to flip it to look for the equivalent resistance. So the 5 and the 10 in parallel have an equivalent resistance of 10/3 of an ohm. Now my fractions are going to get a little bit messy, and this is actually in decimals, so I'll convert to decimals, just make my life easier here. So I've got a 5 ohm resistor, a 10/3 ohm resistor, and a 1.5 ohm resistor all in series. So I get to do the easy rule, 5 plus 10/3 plus 1.5. I get a total resistance of 9.8 ohms. That's the equivalent resistance of the entire circuit. So we might be a little bit off based on our rounding, right? I use 1 decimal place, you can use 2 to get some more accurate results. But so I have a 18 volt resistor connected to a 9.8 ohm, or excuse me, 18 volt battery connected to a 9.8 ohm resistor. So now I'm ready to find the current through the battery. So I take the voltage divided by the resistance, I get 1.8 ohms. I think it's like 1.83 or something. Okay. So 1.8 amps, excuse me, not ohms, amps. So that's the current going through the battery. Now I'm going to go back to my original diagram. Who's along the same path as the battery? Resistor A and resistor C. So in finding this current going through the battery, I just found the current going through 2 other resistors. Very nice. Okay, so I know that 1.8 amps is going through resistor A and 1.8 amps is going through resistor C. Okay, so that's what I have right here. And I'm going to use that current to find the voltage drops across the resistors. So I'm expanding it one step. I'm taking this 9.8 ohms and I'm splitting it back into 5, 10/3, and 1.5. I know that the current everywhere on this path is 1.8 amps. So I want to find the voltage drops across all 3 of these. So the voltage across this 5 right here is its current times its resistance, 1.8 times 5, and I get a 9.2 volt voltage drop across this 5. For the 10/3, I do the same thing. Same current, different resistance. So my voltage drop across a 10/3 ohm. Now remember, this 10/3 is a bunch of resistors in combination, so I'm going to need to use this later. It's 6.1 volts. The voltage drop across the 1.5 ohm resistor is the current going through it. Again, 1.8 amps. 1.8 amps for all 3 of these, times its individual resistance, 1.5 ohms, and I get a voltage drop of 2.7 volts. So I found all these voltage drops across the resistors on the same path as the battery. The loop rule tells me they should add up to 18 volts, and they do. All right. Depending on how you round, you might be off by a 1/10 of a volt, or something like that. Don't panic too much about that, based on how you rounded. So as long as you're pretty close to 18, you should be in good shape. So I'm expanding one more time, right? I'm taking that 10/3 and I'm splitting it up to the 5 ohm B. Right? I called that B earlier because I have 5 ohms, other 5 ohm resistors that are going to show up. So the 5 ohm resistor B and then the 10 ohm. Remember that this 10 is 2 5s in series, but I'm looking for the current that's going through the 5 ohm resistor here and the current that's going through the 10 ohm resistor here. So these are 2 resistors in parallel. They have the same voltage drop across them, and the voltage drop across them is not the voltage across the battery or supplied by the battery, it's the voltage across the 10/3 ohm resistor. So I'm going to use this 6.1 volts as the voltage across these 2 resistors to find the current, right? I'm looking to see how the current gets split up at this junction. So I'm going to use I equals V over R. So I have the voltage drop across resistor B, 6.1 volts divided by the resistance of resistor B, 5 ohms, and I get 1.2 amps, which is less than 1.8 amps, which is good because that's the current that's going into the junction. The current going through the 10 ohm resistor is the same voltage drop, 6.1 volts divided by its resistance. You get 0.61. I rounded it to 0.6 amps, and so 1.2 plus 0.6 is 1.8 amps. So I'm feeling good about my answer because I know there's a current of 1.8 amps going in. There's a current of 1.8 amps going out through the 1.5 ohm resistor, so it gets split up. And again, this is getting twice the current because it's got half the resistance, right? 1.2 amps is going here, 0.6 amps is going here. So the proportion's nice. Kirchhoff's junction rule holds, so I'm still feeling really good about my numbers. Final step is taking that 10 ohm resistor and splitting it back up into the two 5s. Now I know the current going through this entire path is 0.6 amps, right? This 0.6 amps is the current that's going through this path right here. So when I split this up into two 5 ohm resistors again, I know that the current going through resistor D and resistor E is 0.6 amps. So I'm going to use this current and their individual resistances to find the voltage drops across them. So 0.6 amps, they have the same resistance, so they're going to have the same voltage drop. 0.6 amps times 5 ohms is 3 volts. 0.6 amps times 5 ohms is 3 volts. They add up to 6 volts, which is accounting for, my rounding error, is the voltage across the 10/3, right? This whole system right here, this whole parallel system has a voltage drop of 6 volts, 6.1 volts. And so these two in series have a combined voltage drop of 6 volts. So we're good. We've got the voltage drop across each individual resistor, which is what we need, and we have the current that's going through each resistor. So that's what we're looking for. We found the equivalent resistance, the current at the battery, the current through every resistor, and then the voltage drop across every resistor. So one more example, if I have time. Okay, I think I'm in good shape. I've got 17 minutes. I think I can do it. So some circuit diagrams are going to be a little confusing, right? They're not going to be drawn very nicely or as organized as we want them. But if you see a situation like this, you see the 6 ohm and the 12 ohm, they are in parallel, right? So there is a current that goes through here, right? And the current does get split between the 6 and the 12. So these are in parallel. Notice the 4 and the 8 look like they're in parallel, but there's another system kind of preventing us from combining these two resistors, right? So I don't want to combine these two, the 2 and the ohm, or there's a junction in between them, right? So I'm looking at this 6 ohm and the 12 ohm, because if I combine those two resistors, this new resistor system will be in series with the 4, and then I'll just be able to add them up. So that's what I'm doing here, right? I'm taking the 6 ohm and the 12 ohm, and they are in parallel. So I add them up like I do with parallel resistors, right? They got nice denominators. I can find a common denominator. 1 over 4 ohms is my result. Don't forget to flip. The equivalent resistance of the 6 and the 12 is 4 ohms. So I redraw my circuit, combine the 6 and the 12, redraw it as a 4 ohm resistor. Now, as I said at the beginning, we've got two 4 ohm resistors in series. So I get to do the easy addition, 4 plus 4, that's 8 ohms. So again, notice I'm not trying to combine the 2 and the 4 or the 8 with anything else yet. I've got 2 in series. Let me add them up, redraw the circuit with those 2 in series as one resistor. Now I've got two 8 ohm resistors in parallel. I'm going to add them up using my reciprocal rule. 1/8 plus 1/8 is 2/8, which is 1/4. Flip the fraction, I still have my units in the denominator. So the equivalent resistance of the two 8 ohm resistors in parallel is 4 ohms. I'm going to redraw again. Now I'm ready to combine this 2 ohm resistor with that whole mess. See this whole thing? The 4, the 6, the 12, the 8. That whole thing I collapsed to one resistor with an equivalent resistance of 4 ohms. So now I've got the 2 ohm and the 4 ohm in series. Add them up the easy way. 2 plus 4 is 6 ohms. So I'm finished, or I'm almost finished step 1. I've got one battery, one resistor. I'm ready to use Ohm's law to find the current going through the battery. 24 volts divided by 6 ohms is 4 amps. So I'm going to go back to my original drawing and I'm going to say who is on the same path as the 24 volt battery. We only have one this time, that's the 2 ohm resistor. But we know the current through the battery and the current through this 2 ohm resistor is 4 amps. So that tells me that the 4 amps is going to get split here. It's going to get split here again, right? So some portion of the 4 amps is going to go through here, and then whatever that portion is, it's going to get split again between the 6 and the 12, and then there's going to be another portion that goes through this 8 ohm resistor. Expand it one step. Take that 6 ohm resistor, split it back into the 2 and the 4. Find the voltage drops. I've got 2 resistors in series. I know the current going through them is 4 amps, same current as the battery. I'm looking for the voltage drops across the 2 ohm and the 4 ohm resistor. So use Ohm's law again. V equals I times R. Same current, 4 amps, times the individual resistances, 2 ohms. I get an 8 volt voltage drop across the 2 ohm resistor. I get a 16 volt voltage drop across the 4 ohm resistor. 8 plus 16 adds up to 24. Okay, so the loop rule holds. I like my numbers. I feel like I'm doing the right thing here. So I'm going to take that 4 ohm, split it up into 2 8 ohm resistors. Now these are resistors in parallel, so they're going to have the same voltage drop. What's the voltage drop across this 2 8 ohm resistor system? The voltage drop across this thing right here, 16 volts. Okay, so we're not using 24, we're using the voltage drop across the 4 ohm resistor. So using the same voltage drop, 16 volts. 16 volts divided by 8 ohms is 2 amps. These have equivalent resistances, so they're going to get the same current. So the current is equally divided amongst these two paths. So 2 amps plus 2 amps equals 4 amps. So that's good. That's the current that I know is going into the junction. So I'm going to split this 8 ohm back up into the 2 4s in series. Now I know that there's 2 amps going through these 2 resistors. So I need the voltage drops across these two. Right? I know their resistance, I know their current, I'm looking for the voltage drop. So I use V equals IR. I've got 2 8 volt voltage drops. 8 volts across this one, 8 volts across this one. 8 plus 8 is 16. Right? So that's the voltage drop across both of these 8 ohm resistors. Right? So again, I'm feeling good about my answers. They're also very nice numbers in this case, so that also makes it kind of convenient. So final step, I'm taking this 4 ohm resistor and I'm splitting it back up into the 6 and the 12. So I know the current going through this is 2 amps, and I know there's an 8 volt voltage drop. So I'm looking for how the current gets split. Okay, so there's an 8 volt voltage drop across the 4 ohm, which is a 6 and a 12 in parallel. So they have the same voltage drop across them as well, 8 volts. So I'm going to use that voltage drop, divide it by the resistance of each individual resistor to get the current. I want to find out how that 2 amps is split amongst those 2 resistors. So 8 volts divided by 6 ohms is 4/3 of an amp. So there's 4/3 of an amp going through the 6 ohm For the 12 ohm, 8 volts over 12 ohms is 2/3 of an amp. So this resistor is getting 4/3, this resistor is getting 2/3. And that makes sense to me because this is a lower resistance. It's getting more of the current. It's getting twice as much current because it's got half the resistance. And again, the junction rule, 4/3 plus 2/3 equals 2 amps. So a lot of rules, a lot of addition, right? So we have to use Ohm's law different ways to either find the current going through a resistor system or the voltage drop. And we have to keep track of whether the voltage drop is the same because the resistors are connected in parallel, or the current is the same through two resistors because they're in series. So these are some pretty decent basic examples, which I like to use these because they're various combinations of resistors in series and parallel, and it involves, especially this one, involves a lot of steps and applying the rules many times. As I mentioned in the last video, there are more example resistor circuits that I have worked out in the Chapter 18 content folder. So once you tackle those capacitor circuits, go ahead and give those example resistors, circuits a try. Try and work them out on your own based on these examples before you look at the solutions. Again, any questions you have on these examples or the additional examples I uploaded, let me know. Email, Zoom, whatever you want to do. Have fun with these. Take your time. Be careful. And like I said, reach out if you have any questions. Hope everybody's doing okay. All right. See ya.